This time we're going to talk about inferences for matched pairs. That is, the samples are going to be dependent. The requirements will be the samples can be paired up, can be paired up in a sensible way, not just random. The number of pairs must be greater than 30. Or the set of differences must be normally distributed. The pairs of differences, we have them paired up. 72 and 64, 98 and 52, 64 and 41, 81, 72. These students did not study, they took the test, those are their grades. These same students in the next study, they did the next research study, they did study, and those are their grades. Now we can talk about the differences. 8, 46, 29. These numbers must be normally distributed, or the pairs of differences actually, let's say this. There are no pairs of differences. In the bottom, there's just differences. The pairs of values have differences. This pair of value and this pair of value and this pair of value, the pair of values, they have differences. I listed them. 8, 46, 29, they are normally distributed. The pair of values have differences that are normally distributed. Okay, you have two pair of data, sample 1, sample 2, and they're paired up. 72 is paired up with 64. 98 is paired up with 52. If you compute their differences, which I did on the bottom, this list of numbers normally distributed. If that's true, then requirement number 2 has been met. Again, it's easy to use the first part of criteria 2. The number of pairs are bigger than 30. Or the differences of these pairs are normally distributed. Actually, in this case, they can actually be approximately normally distributed. But don't worry about that. You could assume that the normally distributed is enough. It will satisfy condition or requirement number 2. Okay, now, in my opinion, this section requires us to talk about some notation. So let's do that at this point. Okay, so D is the individual difference between a pair of data. Between two values in a single pair. So what I just erased, I had sample 1 and I had 4 numbers, and I had sample 2 at 4 numbers, and underneath, remember I subtracted them and I had 4 numbers down here. That each one of these is what we refer to as a D. Just like the X's are the scores, and X1 is the average of all the X's. So instead of X's, we have D's. How do you get D's? You subtract. Mu sub D, that's going to be the mean of the differences for the population. It's going to be the mean value of D for the population. Mu has always been the population. Now, D bar, that's going to be the mean of the D's, for the sample. Let me come here, please. S sub D, so everything is about the differences. This is the sample standard deviation for the D's. This is the sample standard deviation for the D's. I'm giving you a list of numbers, and I'm saying find the standard deviation. Give you a list of numbers, and I say find the standard deviation. And I call it little s. Well, what are these numbers that I'm giving you? I said I'm giving you a list of numbers. Find the standard deviation. Well, the list of numbers are, the numbers have a special name. They're D's. They're the differences between the pairs. This is the sample standard deviation for all of these. And N is the number of pairs, which is the number of D's. Because for each pair, you subtract them and you get 1 D. You subtract a pair of numbers, you get 1 number. 7 minus 3 is 1 number. It's a number 4, but nonetheless, it's 1 number. All right, let's go to another page and let's talk about, so that's it for notation. Let's talk about the test statistic and the confidence interval. The test statistic, the t-test, is t is equal to d bar minus mu sub d over the standard deviation for d, all of this times the square root of n, where the degree of freedom is back to good old n minus 1. And the confidence interval for the matched pairs is d bar minus e is less than mu sub d, which is less than d bar plus e. And like always, I have to tell you what e is, where e is T sub alpha over 2 times S sub D over the square root of n. So, to find the confidence interval, you need D bar and E. So let's do a couple of problems. One where we need to do a hypothesis test, and one where we have to find the confidence interval. Okay. Now, it's amazing how this is probably going to test out to be true. Some people are very superstitious of Friday the 13th. As a result, they go out and they be stupid, and they have things happen to them that coincide with the myth or things that should happen on Friday the 13th. Like they're going to be unlucky and have an automobile accident. So let's talk about hospital visits from automobile accidents on, I couldn't save that error, on Friday the 6th, versus Friday the 13th of a given month. Now, on Friday the 6th, these are how many people went to a hospital from auto accidents. 9, 6, 11, 13, 3, and 5. Actually, how about 11 again? 11, 3, and 5. And on Friday the 13th, on one particular month it was 13 and another was 14. But the 9 and 13, they were in the same months, 1 week apart. 6 and 12, 1 week apart. 11 automobile accidents on some months on Friday the 6th. The same month, a week later, Friday the 13th, there was 14 accidents, and then 10, and then 4, and then 12. And if you look at these numbers, it seems like there were always, most of the time there was more accidents on the 13th on Friday compared to the Friday before. I say most because on this particular month, Friday the 6th had one more accident than Friday the 13th. So the question is, using a 0.05 significant level to test the claim that the number of hospital admissions due to auto accidents are not affected by Friday the 13th. By Friday the 13th. Okay? We want to put the myth to rest. We're going to go, no, there is no difference. Okay. So, the first thing I would do, and let me do it on top here, is to find D. Let me find the D's. Now, we claim that Friday the 13th should have more accidents. So let's do Friday the 13th minus Friday the 6th. 13 minus 9 is 4. 12 minus 6 is 6 more accidents. 3 more accidents on Friday the 13th. Negative 1 more accident. That is 1 accident less. 4 minus 3 is 1. 12 minus 5 is 7. Now, when it comes to finding the mean and the standard deviation and everything, we're using these numbers in red on the bottom. We're using these numbers. D bar, the average. You add up all the D's and you divide by N. You add up all the D's, you get 20. You divide them by the 6 numbers, and that's 10 over 3, which is 3.33 forever. And if you calculate the standard deviation of those 6 numbers, you would come up with 3.01. So why don't we just say equal then? The standard deviation is 3.01. We're doing everything with respect to the differences. Everything is with the differences. Now, remember, well, let me write TS. The test statistic is T is equal to D bar. Let's write it down. T is equal to D bar minus mu sub D over SD all times the square root of N. Now, we claim, so, HO would be that the means are the same. It's going to mean that the means are the same. That is, the difference of the means is 0. Mu sub D is 0. The claim is that it's not affected. So, the claim says that mu sub D is not affected. It says it is 0. It says it is 0. The claim is that mu sub D is 0. Now remember, for H1, you can't use equal. Well, then it's not equal. That's the claim. That's their alternate hypothesis. It's not equal to 0. Okay? The claim is exactly what the null hypothesis is. All right. So UD is 0. Well, D bar, we just worked it out. It's 3.33 divided by the standard deviation, which we calculated from the data. I hand waved there. That's way earlier in the video where we calculate standard deviation given the data. And then we multiply this by the square root of N, which is 6. And if you were to crank out that, what you would get is 2.7126. That's the test statistic. Now, let's find out what T is. We know that the degree of freedom is N minus 1, which is 5. And where can I put this? I guess I have to put it in right here. This is a two-tailed test, and we want to use 5% significant level. That means each tail gets 0.025. It's a two-tailed test, 0.025. And when you look up the degree freedom, you look in the left column by 5, and the top heading, two-tail, 0.025, it turns out that the T value is negative 2. It's not coming. You really can't see it, so I'll put it on top. Negative 2.5 571, excuse me. Negative 2.571. The t-value right here is positive 2.571. So those are the cutoffs. That's the cutoff. Right here, t is 2.571. But our test statistic was bigger. It was bigger. It was 2.7. 2.7126 versus 2.571. Okay, so in here we accept HO. So we are going to reject HO. We are going to reject HO. Okay, I'm going to put this right here in red. We are going to reject HO. But HO happened to be the claim. So there is sufficient evidence to justify the rejection of the claim. So there is sufficient evidence to warrant, to justify the rejection of the claim of no effect. To justify the rejection of the claim. It turns out that people do have more accidents. According to this study, people do have more accidents on Friday the 13th. And it is not because one really should be, because there is something strange going on in Friday the 13th. The only thing strange going on, in my opinion, the only thing strange going on Friday the 13th is that people behave differently, and as a result, strange things happen to them. Let's face it, you act differently, strange things are going to happen. That is, I don't believe that Friday the 13th in itself causes more accidents. It's just a random day. We can now say Friday the 17th is a bad day, an unlucky day, and if people really started believing this, there'll be less accidents on Friday the 13th and more on the 17th. Okay, new problem. An experiment was performed twice with the group. Okay, now the experiment tested how long it took them to do something, to complete some task. Both times were recorded. It was the first time and the second time for each member of the group. Okay, so you have the first time some experiment was done, some task was done, and then the second time. And we recorded the time for each person in the group. The first person took them 30 minutes the first time, 30 minutes the second time. And then 19 and 6, and then 19 and 14, and 23 and 8, and 29 and 15, make it 14, 29 and 14, etc. 29 and 14 minutes or seconds, it doesn't matter. 178, maybe the units are minutes. Okay, 42 and 14, 42 and 14, and 20 and 22, and 12 and 17, 12 and 17, and 39 and 8, and 14 and 11. Okay, that's the data. Actually, there's more. 81, 17, 31, 31, and lastly 32. Group, second time, sorry, 30, 14, 17, and 15. So I ran out of space and I'm continuing. This is still the first time and the second time. So there were 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 people in each. There were 15 people, and the times were recorded the first time that they did this experiment, and then the second time they did the experiment. They did some task. And some people, they get better as time goes on. You do something more than once, you get quicker at it. Now, turns out that D bar is 22.27, and the standard deviation of the D bars is 32.78, and like I said, N is 15. Now, if you wanted to calculate this, how would you do it? Well, you do 30 minus 30 is 0. That's a D. 19 minus 6 is 7. 19 minus 14. 23 minus 8. These numbers that I'm writing down now, those are the D values. These are the D values. 3. Excuse me. 51, 3, 14. Excuse me, 17. If you were to add up these 15 numbers, divide by 15, excuse me, you would get D bar. And if you calculated the standard deviation of just the numbers in the boxes, you should get 32.78. Okay. Now, the problem is asking to construct a 95% confident interval for the mean of the differences. The mean of the differences. Okay. So, basically, we have to calculate T sub alpha over 2. Well, alpha, if it's 95%, you have 5% left over, divided by 2, you get 0.025. And the degree of freedom, df, is n, 15, minus 1 is 14. If you go to df 14 on the left column, and you go to two-tail 0.025, 15, that number right there, that's the number you're looking for. And that number is 2.977. Actually, one change I'm going to make. I still want to use that number 2.977, but that's a 99%. So alpha is 1%. Alpha is 1 minus the confidence level. Okay. And 1 minus 99% is 0.01 divided by 2. You get not 0.01, but 0.005. So under in the chart, you go to two tails. You look under two tail, 0.005, and you look down there, and you look across at 15 because that's the degree of freedom. And right here, that's where you're going to find 2.977. So that's the t value. That's t alpha over 2. Now we need that to find e. Okay, our goal right now is to find e. And remember that e is equal to t alpha over 2 times s sub d over the square root of n. So we have everything. We have t alpha over 2. We have s sub d, 32.78, 32.78, and we divide this by the square root of n, where n is 15. And we crank this through with our trusted calculator, and like magic, we get some number. We get 25.2. And that's where everything comes together, because the confidence interval is d bar minus e is less than the population mean, is less than d bar plus e. Well, I have d bar, it's 22.77. 22.77, and now I take away e, which is 25.2, and that's less than ud, and that's less than d bar, which is still 22.77, plus e, which is still 25.2. And kind of ran out of room. Wish I can lower that page a little bit. But if you do this mathematics right here, you should get negative 2.93. And that's less than mu sub d. And if you do this math, you should get 47.97. 47.97. 44.97. Okay, if you couldn't see that, I'm sorry, but you know how to add 22.77 plus 25.2. So that's their confidence interval. And that finishes this section. Okay, good luck with it.